Welcome to the AI Coach by Anil Nathu. Today we're taking a deep dive into some really groundbreaking research. It's tackling one of the trickiest but honestly most vital challenges in autonomous driving and 3D perception generally. We're talking about how to make AI see more clearly, more reliably, especially in those tough situations like blurry, distant objects or maybe completely unfamiliar environments. We're unpacking a paper titled DiffRefine, diffusion-based proposal-specific point cloud densification for cross-domain object detection. Now, this work comes from a brilliant team, folks from the University of Oxford and Microsoft Research. We're talking Sangyin Shin, Yuhang He, Xin Yu Ho, Samuel Hodgson, Andrew Markham, and Nikki Trigoni. Our mission today for this deep dive is to really get under the hood and understand how DiffRefine uses this really innovative approach. It's inspired by diffusion models, those incredible AI image generators, the ones that create stunning visuals from, well, what seems like just noise. DiffRefine uses that kind of idea to dramatically improve the robustness of 3D object detection. We'll explore why this matters so much, especially for real-world safety. We'll dig into how this ingenious system actually works, step by step, and, importantly, what does it all mean for the future of reliable AI vision? By the end, you'll walk away with, I think, a really clear and comprehensive understanding of this complex topic and some of its frankly surprising implications for how AI perceives the world around us.
The blurry problem. Why current AI struggles with 3D vision.
Okay, let's unpack this core challenge then. Imagine you're in a self-driving car. Just picture it. It's maybe trying to spot a pedestrian way down the road. It's drizzling, maybe getting dark, or perhaps there's a vehicle partially hidden by heavy fog. What makes that task so incredibly difficult for an AI? Especially when that same car moves from, say, a sunny, well-mapped test environment to a bustling, unfamiliar city street. Maybe it even has different sensors than it was trained on. I mean, it sounds almost simple to us as humans, right? But the real world is just inherently messy and unpredictable for AI.
You've hit on something critical there. What's truly fascinating and a huge hurdle is this concept of domain shift. It's a significant bottleneck, honestly. It can be a real showstopper when you're trying to deploy AI systems in the real world, particularly when we're dealing with 3D point clouds. Now, for those who might not be familiar, 3D point clouds, they're essentially these vast collections of data points in three-dimensional space. They're gathered by sensors like LiDAR, that stands for light detection and ranging. Think of it like a super detailed 3D scan of the car's surroundings. Millions of points mapping out everything. The problem, the real headache, arises because these AI systems, they're typically trained in one very specific environment. Let's say a system learns to recognize cars, pedestrians, cyclists, whatever, in sunny California. It uses data from a particular high-resolution LiDAR sensor, maybe a 64-beam LiDAR, which generates very dense, detailed point clouds, lots of data points for every object. But then you need that same system to perform reliably in a completely new domain. And that could be, say, a rainy London street, captured by a different type of sensor, maybe a 32-beam LiDAR, which produces significantly sparser data. Fewer points per object, harder to see the shape. Or it could be even more complex, like an environment scanned by multiple LiDARs, all creating different point densities in different areas. The core issue, and the authors, Sangyin Shin and his colleagues, they state this very clearly in their research. The robustness of 3D object detection in large-scale outdoor point clouds degrades significantly when deployed in an unseen environment due to domain shifts. End quote. Now, this isn't just some minor technical glitch or a small drop in accuracy. It has critical safety ramifications. For instance, if an autonomous vehicle system misses an object entirely, what we call a false negative, that can have, well, severe consequences. It could be anything from a minor bump to something far, far worse. So ensuring reliable detection across these vastly diverse conditions, these different domains, it's absolutely paramount. It's non-negotiable for safety.
Right, so it's not just the weather changing or the city looking different, it's the actual technology, the sensors themselves, creating fundamentally different kinds of data for the AI to interpret. Beyond this general domain shift idea, what are the really primary factors causing this degradation in performance? When an AI moves from its nice, clean training data to the messy real world, is it mostly about the sensors?
Yeah, you've hit on a critical point. Several factors contribute, and they often interact, sort of compounding each other, making the problem even tougher to solve. Firstly, as you mentioned, there are significant variations in object sizes and sparsity caused by different sensors. A LiDAR with fewer beams, let's say a 32-beam unit compared to a 64-beam one, it will naturally produce a much sparser point cloud when scanning the exact same scene. Just fewer laser lines hitting the objects. This means objects, especially smaller ones or ones further away, will appear with far fewer data points describing their shape and position. Makes them inherently harder to delineate and recognize. Secondly, And this is truly crucial, especially for autonomous systems dealing with road safety. There's the diminishing point density on object surface due to the distance from the sensor. Basically, the further away an object is, the fewer LiDAR points actually hit it in return. So imagine that car way down the road from the sensor. Its representation in the point cloud becomes incredibly sparse. We're talking maybe just a handful of scattered dots. It's almost like trying to recognize a complex shape from just a few stars in a constellation. It's incredibly hard for the AI to discern its form, let alone classify it confidently as a car. The paper actually highlights this visually in their Figure 1, showing how these distant objects essentially become featureless blobs of very few points. This extreme sparsity makes it incredibly difficult for the AI model to extract meaningful characteristics or features needed for recognition. And then you combine that with changing environmental structures, different types of roads, buildings, maybe even different foliage patterns that might also confuse the system, and you see why it's such a hard problem.
Wow, okay. It really does sound like searching for a needle in a haystack, but the haystack itself keeps changing its shape and density, and sometimes the needle is like almost invisible. So given this really tough challenge, the domain shift, the extreme sparsity, especially with distant objects, what have researchers tried so far? What were the sort of go-to methods before something like DiffRefine came along?
That's a great question. Historically, the existing methods for domain-adaptive 3D detection have generally fallen into two main categories. Each has its own strengths, absolutely, but also, more importantly for our discussion, significant limitations, particularly when you're dealing with these truly sparse or distant objects where the data is just minimal. The first category is what we can call data augmentation-based techniques. The core idea here is to try and make the AI model less sensitive, or insensitive as the paper says, to these variations in point cloud sparsity that happen across different domains or distances. How do they do it? Well, the core idea is quite clever. During the training phase, you simulate sparsity. For example, you might take a nice, dense point cloud of a nearby car, lots of points defining its shape, and then you strategically, maybe randomly, remove points from it. This process, often called subsampling or point dropping, creates a sparser version of that same object. It mimics how that car might appear if it were much further away, or perhaps scanned by a lower resolution sensor. The detection model then learned, hopefully, to be robust to these density variations, because it's been exposed to a wider range of sparse representations during its training. It's a bit like training a human to read blurry signs by showing them lots and lots of examples of blurry signs. You hope they generalize. However, and this is a big however, the researchers behind DiffRefine explicitly pointed out a key limitation here. They state, the augmentation is usually only effective on already dense objects, which are usually close to the sensors. Why? Because, as they explain, since the upsampling is based on the interpolation of existing points, the distant objects, which are usually partially visible, do not get the maximum benefit from the techniques. Think of it this way. If you have a nearly complete drawing, and you just erase a few lines here and there, you can probably still easily infer the full picture. Your brain fills in the gaps. But if you only start with a few scattered dots like that distant car trying to fill in the gaps by interpolating between almost nothing, well, it just doesn't magically create the rich, detailed features needed for accurate detection. If the initial input is already extremely sparse, these augmentation methods simply hit a wall. They can't invent information that isn't there, even implicitly. Okay, so the second main category is prototype-based techniques. These methods take a slightly different approach. They involve the AI learning prototypes of objects, often captured from multiple viewing angles or in various states of completion. So imagine the AI doesn't just learn one canonical car shape. Instead, it learns specific prototypes like car viewed from the side, car from the front quarter, maybe even car with partially visible wheel, or car occluded by a bush. The idea is that if a partially seen or sparsely represented car in the new target domain matches one of these learned prototypes, even roughly, the system can identify it. This approach is helpful for dealing with partial occlusion and different viewpoints, but once again there's a significant limitation, especially concerning sparsity, which the DiffRefine paper notes. They say the prototypes also struggle to reduce the false negative detections when the objects are featureless due to sparsity. Basically, if the input is too sparse, just those few scattered dots representing that distant car we keep mentioning, it simply doesn't resemble any known prototype enough to trigger a match. It doesn't matter how many partial views or occluded examples the AI has learned. If the distinguishing features are fundamentally absent from the input data because it's so sparse, the prototype matching just fails. You can't match something to a template if the something barely exists in the data.
Okay, so both augmentation and prototypes have their merits, especially when there's some reasonable amount of data to work with. But they both seem to hit this fundamental wall when objects become truly sparse and lack their key distinguishing features, particularly the distant ones. It sounds like they're just not equipped to essentially invent or reconstruct the missing information needed for confident detection in those extreme cases. Is that precisely where DiffRefine comes in? Does it aim to bridge this crucial gap by somehow, well, inventing or reconstructing that missing data to make the invisible visible?
Precisely. You've nailed the core motivation. The authors highlight a really key observation, likely from analyzing failures in existing systems. They noted that often, detection proposals already contain the accurate bounding boxes, but with relatively low objectness score predictions, which lead to false negatives. Let me break that down. In a typical two-stage AI detection pipeline, which is common in 3D perception, the first stage does a quick scan and generates initial proposals. These are basically rough bounding boxes indicating where objects might be located. And often, this first stage is actually pretty good at locating the object. The box might be in roughly the right place and the right size. But because the points inside that proposed box are too sparse or too featureless, think back to that distant car, the system isn't confident enough to confirm, yes, that's definitely a car. This uncertainty results in a low objectness score. And if that score falls below a certain threshold, the system incorrectly classifies it as background, or just noise resulting in a dangerous false negative. The car is there, the initial guess was right, but the system lacked the confidence to make the call. DiffRefine's core goal, its central premise, is to tackle this specific problem head-on. It aims to reinforce those features by generating points on object surface to make them straightforwardly recognizable. It takes those low-confidence proposals, the ones that are probably right but too sparse, and it actively adds detail, fills in the gaps, making them much clearer and easier for the subsequent stages of the AI to process and confirm. This kind of targeted enhancement, boosting the confidence in detections that would otherwise be missed, is exactly the kind of critical perception capability we explore here at the AI Coach by Anil Nathu, turning potential misses into reliable detections.
DiffRefine's ingenious approach, densifying the invisible.
This is fascinating. It raises a really important question, though. How does DiffRefine actually do that?
Yeah.
How does it generate points and make these sparse objects recognizable? We hear a lot about diffusion models, especially in the context of AI art, generating these incredible photorealistic images from just text prompts, seemingly creating something from noise. What's the core intuition behind using a diffusion model here? For something as concrete and safety critical as 3D point clouds and autonomous vehicles, it feels like a pretty significant leap from generating artistic images to enhancing real-time perception.
That's a fantastic question, and it really gets to the heart of the innovative leap this research represents. The core intuition for adopting diffusion models in DiffRefine is actually twofold, as the paper details quite clearly. First, they propose a really interesting way to think about the problem. They hypothesize that sparse points on object surfaces can be considered to be a noisy representation of dense object points, which can be recovered by iterative denoising. Let that sink in. Think of it like taking a very blurry or grainy photograph. The blur and grain are essentially noise obscuring the clean, sharp image underneath. In this analogy, the sparse points of that distant car, they're treated as the noise. And the goal of the diffusion model is to act like a sophisticated denoising algorithm to progressively remove that noise, the sparsity, and reveal the clean, dense, and complete object structure hidden underneath. It's a process of reconstruction, starting from a degraded signal. The second part of their intuition relates to how this recovery happens. They argue that diffusion with multiple steps allows effective learning in challenging point cloud generation, rather than conventional densification in one step. What does that mean? Instead of trying to make a single, potentially inaccurate, all-or-nothing guess at what the dense object should look like based on the sparse input, diffusion works iteratively. It refines its output over several steps. It learns to fill in the missing details progressively, adding points or adjusting existing ones gradually. You can think of it like an artist starting with a very rough sketch and then adding more and more detail, refining lines and shapes over several passes until a detailed painting emerges. This iterative refinement makes the whole process much more robust and ultimately more accurate, especially when you're dealing with the significant levels of sparsity and ambiguity common in real-world LiDAR data from distant objects. The multi-step approach allows for a more nuanced and controlled reconstruction of complex 3D shapes, even when starting from very minimal information.
Okay, so it's not just a single magic trick, but a careful, step-by-step reconstruction process. Almost like an artist patiently bringing a detailed image out of a rough sketch, or maybe like developing a photograph to stages. How does this all fit into the bigger picture then? What does the overall process look like from start to finish? And crucially, how does DiffRefine integrate into an existing, often quite complex, 3D object detection pipeline? Does it replace parts or add to them?
Great question. The overall pipeline is actually quite elegant in how it integrates DiffRefine. The paper illustrates this clearly in their figure 2. DiffRefine is positioned as a critical intermediate module. It strategically sits right between what they call the first stage detection and the second stage refinement. So think about a typical two-stage 3D object detection system. The first stage does a quick pass over the entire point cloud. It generates those initial box proposals we talked about. These are rough 3D bounding boxes suggesting where objects might be located, often along with some broader spatial features describing the scene context. These first stage proposals can be numerous and often include low confidence guesses for sparse objects. DiffRefine takes these initial proposals, particularly the uncertain ones, as its input, and then it works its magic to make them much clearer and more detailed before passing them on. So given these initial box proposals, DiffRefine performs 3 key steps in sequence. These steps transform those sparse, often low confidence guesses into dense, highly recognizable object representations that the second stage can then confidently classify and refine. Step A is point extraction and size agnostic voxelization. This first step is all about preparation and normalization. Its purpose is to take the raw, sparse points that happen to fall inside each proposed bounding box and get them ready for the core diffusion process. A key challenge the researchers identified is that the variance in object sizes across domains negatively affects the performance. Think about it. A small car seen up close by a high-res lidar might generate a large cluster of points, while the same car seen far away by a low-res lidar might appear as just a few points. This size variation can confuse the AI. To counteract this, they first extract all the points located inside each proposed box. Then, crucially, these extracted points are transformed into what they call a normalized box view, NBV. This transformation cleverly rescales and potentially reorients the points within the box so that the resulting representation becomes size agnostic. The system essentially looks at the object within its box in a standardized way, regardless of its original apparent size or distance. This means the AI doesn't get confused if a car appears larger or smaller due to different sensor perspectives or ranges. After this normalization, these points, still potentially sparse, are then voxelized. This means they're placed onto a fixed size 3D grid, maybe 32 by 32 by 32 tiny cubes or voxels. This converts the irregular scattered point cloud within the box into a regular structured input format that the diffusion model can easily process in the next stage. It ensures consistency. Step B is the core. Proposal-specific point generation with diffusion. This is really where the magic happens, where the diffusion model gets to work densifying the object. The underlying idea, as the authors explain it, is pretty intuitive. Objects of the same category, such as car and pedestrian, share similar physical features. They have an underlying structure, so even if you only have a few sparse points representing a car, those points still contain some information, some hints about its fundamental structure, perhaps the rough outline of its body, the general aspect ratio, or the approximate locations where wheels should be. These shared underlying geometric features are what the diffusion model is trained to expertly leverage and build upon. Okay, so how does the diffusion part actually work in this context? The voxelized sparse points from step A, which represent the object in that normalized grid, are treated as the initial noisy sample, let's call it time step T, the most noisy state. The diffusion model's task is then to iteratively denoise this voxel grid step by step, gradually adding or refining points until it generates a clean sample at time step 0, the least noisy state. This clean sample represents the dense, complete set of points that should constitute the object. They apply this denoising principle directly to the voxel grid, aiming to generate enough meaningful features within the grid to drastically reduce those frustrating false negatives we discussed earlier, tuning uncertain blobs into recognizable shapes. How is it trained? Essentially, they teach the model what a dense object should look like. During training, they provide examples of complete dense objects, the ground truth. The model learns to reverse the process of adding noise. It learns how to remove the sparsity noise to get back to the clean, complete object. Now, crucially, the paper emphasizes that this is differentiable generation. This is a key technical detail. A simpler approach might have been to just train a model to classify each tiny voxel cube in the grid as either occupied by the object or empty, a kind of dense grid classification. However, the authors point out that this simpler classification approach is problematic. Why? Because classification outputs are typically discrete, yes, no, occupied, empty, which makes them less suitable for the smooth, multi-step, iterative denoising process that defines diffusion models. You need something more continuous. So instead of just classifying voxels, DiffRefine learns to predict offsets. These are essentially 3D vectors. For each point or potential point location, the model predicts how much does this point need to move, or where exactly should a new point appear to best fill in the missing parts of the object and make it denser and more complete. This approach of predicting continuous offsets is differentiable. This is critical because it allows gradients, information about errors, to flow smoothly back through the generation process during training. This enables joint optimization, where the diffusion model learns not just to generate points, but to generate points in a way that directly helps the downstream detection task. It allows for smooth, iterative refinement. Let me give you an analogy for the training process. Imagine you start with a perfect, complete 3D model of a car. That's your ground truth, the clean sample. To train the diffusion model, you artificially introduce noise by randomly removing points or voxels, making it sparse, step by step. This simulates the noisy, sparse inputs you'd get in the real world. Then, the model's job is to learn the reverse process. Given a noisy, sparse version at any step, predict the offsets needed to move closer to the less noisy version from the previous step. It learns to effectively denoise the sparse representation step by predicting how to fill in those missing parts. During actual inference, when the system is running in a car, you start with the real-world sparse input from step A. Figure 3A in the paper shows this. The trained diffusion model then iteratively predicts these 3D offsets. It uses what they call a differentiable warping operator, essentially a smart way to apply these predicted movements to continuously shift existing points and introduce new ones, effectively densifying the object within the voxel grid over several steps. Figure 4 in the paper beautifully illustrates this iterative process. You start with just a few scattered dots, labeled general step 1. Then, over subsequent steps, like general step 4, general step 8, you see the object, whether it's a car or pedestrian, gradually taking shape, becoming a coherent, dense form. It's quite remarkable to see it emerge. This innovative use of diffusion, guided by these learnable offsets, truly exemplifies the kind of powerful insights that you can gain by digging into advanced AI concepts, maybe with resources like the AI Coach by Anil Nathu. Step C is points region correlation and box refinement. Now, this step addresses a critical challenge inherent to almost all powerful generative models, including diffusion: the problem of hallucination. What's hallucination in this context? Well, if the diffusion model becomes too good, too creative at generating points based purely on the inferred shape of an object category, like car, it might start hallucinating, generating a beautifully dense car shape even when the initial sparse input came from, say, just a random patch of empty road, or maybe some foliage that vaguely resembled a car shape initially. The researchers explicitly mention seeing an erroneously generated car instance appears despite not being warranted without this step. This is obviously a massive safety concern for autonomous vehicles. You definitely don't want your car reacting to phantom vehicles. So how do they prevent this? DiffRefine implements a crucial safeguard: spatial context fusion. The core idea is brilliant. Fuse a spatial context to the generated output. This means the newly generated dense object points aren't considered in isolation. Instead, they're evaluated in accordance with their surrounding environment. The system asks, does it make sense for this object, like a car, to be here, like on a road? To achieve this, DiffRefine cleverly takes the highly detailed spatial features learned during the first stage detection. These features, often called FRPEV because they represent the bird's eye view, capture information about the broader scene, like where the road is, where buildings are, etc., and it combines them with the newly densified object features, FFE, generated by the diffusion model in step B. This fusion happens using a sophisticated mechanism called cross-attention. You can think of cross-attention like a smart filtering or selective focus mechanism. It allows the model to intelligently weigh and combine information from both sources, the broad scene context and the specific object details. It helps the model decide which aspects of the surroundings are most relevant for confirming the object's presence, type, and precise location. For instance, seeing road markings nearby would strongly support the presence of a generated car. The impact is significant. As figure 6 in the paper visually demonstrates, including the spatial context, which they call FIGN, the fused feature, dramatically improves the final detection output by preventing those dangerous false positives, the hallucinations. A generated car shape is now considered much more plausible if it aligns with its likely surroundings. A car is likely to be located near a road, as the paper puts it simply. This final, context-aware, densified feature then feeds into the standard second-stage refinement modules. These modules, common in many detection pipelines, take this enriched information to produce the final, highly accurate bounding box and the object's classification, car, pedestrian, etc. This crucial step ensures the generated points lead not just to denser objects, but to reliable, contextually grounded detections, making sure the AI doesn't just see things, but understands them within their real-world environment.
Right, that makes perfect sense. So it's not just blindly making objects denser based on some learned template. It's making them denser intelligently, constantly checking if the result actually fits within the context of the surrounding scene. That seems absolutely key to preventing potentially dangerous mistakes or hallucinations. What is this whole intricate process, the normalization, the iterative diffusion generation, the context fusion? What does it all mean for how the entire model learns during its training phase? How do all these different components, with their own goals, learn to work together effectively?
That's a critical aspect. The overall training strategy. The researchers designed it for joint optimization. This essentially means that all the different parts of the system, the initial first stage detector, the DiffRefine module itself, and the final second stage refinement network learn together simultaneously, reinforcing each other for maximum overall effect. How does this work technically? They combine the different loss functions, mathematical ways of measuring errors from each part. So you have the standard losses from the first stage detector, let's call them L first, which typically penalize errors in proposing initial object locations and rough sizes. You also have the standard losses from the second stage refinement module, L second, which penalize errors in the final precise classification, is it definitely a car, and the exact 3D bounding box position and orientation. And now DiffRefine introduces its own new loss function, the diffusion loss, LDiff. This loss specifically encourages the accurate step-by-step generation of dense points that match the ground truth object shapes. During training, the system tries to minimize the sum of all these losses, L first plus L diff plus L second. This joint optimization is incredibly important. It ensures that the DiffRefine module isn't just learning to create pretty, dense point clouds in isolation. Instead, it's learning to generate points in a way that directly helps the first stage make better proposals and, crucially, helps the second stage perform more accurate final classification and localization. It forces all parts of the system to cooperate. For example, the gradients, error signals from the final refinement stage, can flow back not only through the refinement network itself, but also through the DiffRefine module, thanks to that differentiable generation, and even back to the first stage. This helps the entire system learn a much more coherent and holistic understanding of objects, how they appear in various states of sparsity, and how they relate to their environmental context. It leads to a much more robust and capable overall AI model than if each part were trained separately. It's a really synergistic learning process.
Proving the power DiffRefine's performance in practice.
Okay, this is where it gets really interesting, isn't it? We've talked about the theory, the clever mechanisms, the iterative denoising, the context fusion. It all sounds incredibly promising on paper. But how well does DiffRefine actually perform when you put it to the test? In the messy, unpredictable real world, or at least in realistic simulations of it. What kind of experiments did the researchers conduct to rigorously prove its effectiveness, especially given all those challenges we discussed earlier, the different sensors, the varying environments, the dreaded domain shift?
You're absolutely right. The proof is in the pudding, as they say. And the team behind DiffRefine conducted incredibly extensive adaptation experiments to validate their approach. They didn't just test it on one dataset. They used 3 widely adopted and challenging benchmark datasets, specifically chosen because they represent different LiDAR sensor characteristics and diverse environmental conditions. This makes their results much more compelling and indicative of real-world applicability. So first, they used the Kitty dataset. This is a very well-known benchmark in the autonomous driving world. Its data was captured using a 64-beam Velodyne LiDAR, which generally produces relatively dense point clouds. Think of this as a sort of standard, relatively data-rich baseline. Second, they used new scenes. This dataset is different. It uses a 32-beam LiDAR. This inherently produces sparser point cloud data compared to Kitty. Testing on new scenes is crucial because it directly probes the model's ability to handle lower-resolution sensor data, a common scenario in many real-world systems. And third, they brought up the big guns, the Waymo Open dataset. This is a massive dataset, significantly larger than Kitty or new scenes, and it features a sophisticated multi-LiDAR setup. It includes one mid-range 64-beam LiDAR, similar to Kitty's, but also 4 short-range LiDARs, which likely have different characteristics. This dataset represents incredibly complex real-world variability, diverse scenes, varying object densities, complex interactions, much closer to what a car would actually encounter driving on public roads. Now, for the comparison, they didn't just compare DiffRefine to simple baselines. They pitted it against several recent cutting-edge 3D domain adaptive detection methods specifically designed to tackle domain shift, like ST3D, DTS, and Group XDA. These are strong competitors. They also showed DiffRefine's versatility by integrating it with two popular underlying base detectors, second IOU and point pillars. This demonstrates that DiffRefine isn't a standalone detector, but rather an enhancement module that can potentially boost the performance of various existing systems. The overarching goal of these experiments was clear: to rigorously evaluate how well DiffRefine could bridge the domain gaps in three distinct and challenging adaptation scenarios, mimicking real-world deployment challenges. These were: 1. Adapting from Waymo, rich multi-lidar source, to new scenes, sparser target. 2. Adapting from Waymo, sparse source, to Kitty, denser target. 3. Adapting from Waymo, rich source, to Kitty, denser target. While their initial focus, like much of the field, was on detecting cars accurately across domains, they crucially also pushed the limits by testing DiffRefine on smaller, often much sparser objects like pedestrians and cyclists. Detecting these vulnerable road users reliably, even when they appear as just a few lidar points, is arguably an even greater challenge and absolutely critical for safety. And how do they measure success? They use standard, well-accepted metrics in the field, primarily APBE, average precision in bird's eye view, which measures how well the system detects objects looking down from above, and AP3D, average precision in 3D, which is a more stringent measure of its full 3D detection accuracy, considered position, size, and orientation in 3D space.
Okay, that sounds incredibly thorough. Multiple challenging datasets, comparisons against state-of-the-art methods, different base detectors, and testing on difficult object classes like pedestrians and cyclists. That really sets the stage. So after all that sophisticated engineering and this extensive, rigorous testing, what were the results? Did DiffRefine actually deliver? Did it make a tangible, measurable difference in how well the AI could see in these challenging, low-data, cross-domain situations?
Absolutely, it delivered. The quantitative results presented in their tables 1 and 2 are remarkably clear and show significant consistent improvements across the board. It wasn't just a minor edge, it was often a substantial gain. Looking at the overall performance of car detection, DiffRefine consistently outperforms the baseline ST3D series, ST3D being a well-regarded prior method. And even more impressively, it frequently exceeds the previous best-performing method, which in their comparisons was often Group XDA across all three adaptation scenarios and when used with both base detectors, second IOU and point pillars. Let me give you a concrete example. In the challenging Waymo Kitty adaptation scenario, going from the rich Waymo data to the different Kitty environment, when using the second IOU base detector, DiffRefine achieved an improvement of 0.87 percentage points in APBV and a solid 1.54 percentage points in AP3D over the previous best, Group XPDA. Now, these might seem like small numbers if you're not familiar with these benchmarks, but in the highly competitive field of autonomous driving perception, where every fraction of repentant accuracy matters for reliability and safety, these represent substantial and meaningful gains in real-world performance. And the gains were even more pronounced sometimes. For instance, using the point pillar's base detector in that same Waymo Guinea scenario, DiffRefine outperformed Group XBA by a very notable 6.29 points in APEV and 1.73 points in AP3D. These aren't just minor tweaks. They indicate a tangible boost in the system's core capability to handle domain shift. What's perhaps even more impressive, and certainly crucial from a safety perspective, is its performance on the pedestrian and cyclist categories, as shown in Table 2 for the New Scenes Kitty adaptation. Remember, these are smaller objects, often represented by very few points, making them notoriously difficult to detect reliably, especially across domains. Here, DiffRefine demonstrated truly superior performance. It exceeded the previous best-performing method by a significant margin. 1.97 points in APBEV and 1.43 points in AP3D for pedestrian detection, and 1.35 points in APBEV and 0.81 points in AP3D for cyclist detection. This is vital. Improving the detection of these vulnerable road users, especially in challenging conditions or when they're far away, is paramount for the safety case of autonomous systems. This result really underscores the practical impact of DiffRefine's densification approach. It shows it's not just helping with big objects like cars, but also significantly improving performance on these harder, arguably more critical detection tasks. This is exactly the kind of advancement that understanding tools like the AI Coach by Anil Nathu can help you appreciate, connecting benchmark numbers to real-world safety implications. And, beyond just the numbers in the tables, the qualitative results they show in Figure 5 really drive the point home visually. You can actually see the difference. They show examples where DiffRefine successfully detects objects, cars, pedestrians that other state-of-the-art methods struggle with or miss entirely in the same scene. For instance, they mentioned that DTS, another method, is pretty good at handling density variations, but often struggles with accurately estimating the 3D orientation, the rotation, of distant objects. Group XPDA might be better with diverse shapes, but still tends to have more false negatives, missed detections, when objects become really sparse. In contrast, the visualizations for DiffRefine show its clear ability to densify the sparse points of objects regardless of distance. This leads directly to much more accurate detection and localization of those tricky objects that almost seem to vanish into just a few points due to distance. Seeing these side-by-side comparisons where one method misses a distant car in DiffRefine clearly outlines it provides compelling, tangible proof of its effectiveness for real-world scenarios. It's literally seeing objects emerge from what looks like almost nothing in the raw data. That's powerful.
That visual proof really is powerful. Seeing those examples where objects just pop into view with DiffRefine while other methods fail, it makes the quantitative gains much more concrete. But beyond the impressive overall performance, what about the specific design choices within DiffRefine? You mentioned the iterative generation, the context fusion. Did they conduct experiments to really drill down and test which parts of their proposed system were most critical to its success? Could they remove a component, for example, without a significant drop in performance? This kind of ablation study is often where the true engineering insights lie, right?
Absolutely right. The researchers conducted a series of meticulous ablation studies, which are crucial for this exact purpose. They systematically took apart the different components of DiffRefine to measure their individual contributions to the overall performance improvement. This helps us understand why it works so well, not just that it works. Okay, let's start with the impact of differentiable warping and spatial context, FDGA. They looked at these two key innovations together in Table 3. First, to test the importance of that spatial context fusion. Remember, using the surrounding scene information. They ran an experiment where they directly fed the densified object output from the diffusion model straight into the refinement module without merging it with those broader scene features, FBD. The results were striking. Excluding the spatial context, FGG led to the largest single performance drop they observed in their ablations, a decrease of 1.58 points in APBEV and 1.06 points in AP3D. This strongly confirms our hypothesis. FG encodes spatial context, which can provide additional signals for refinement to avoid false positive detection. That context is vital for preventing hallucinations. Figure 6 visually reinforces this, showing how including Phrygian prevents the model from erroneously generating a car where there shouldn't be one. Context matters hugely. Second, they tested the importance of the differentiable nature of their generation process. They essentially broke the continuous gradient flow back through the diffusion model during training, making the point generation non-differentiable from the perspective of the overall end-to-end optimization. This also negatively impacted performance, though not as much as removing the context. This proves the benefit of that joint optimization we discussed. Allowing the error signals from the final detection to flow back and influence the point generation process itself helps the whole system learn more effectively. Unsurprisingly, the best performance is achieved when both innovations of the differentiable generation and the spatial context fusion are used together. It highlights their synergistic effect. They work better together than either one does alone. Next, they examine the impact of generation steps. Remember, DiffRefine uses an iterative diffusion process. So a natural question is, how many steps are enough? Or are more steps always better? They vary the number of denoising steps used for the point generation, typically from 2 up to maybe 8 or 10 steps. Figures 4 and 7 in the paper show the results. They found that increasing the steps from 2 up to 6 consistently showed improved accuracy, specifically AP3D. The generated objects become progressively more coherent and detailed. However, the improvements started to plateau or even slightly decrease after 6 steps. They conclude, the performance reaches the best when using 6 steps for denoising. What's the trade-off? Each additional denoising step adds a tiny bit more computational time. They measured it at about 0.02 seconds per step on their hardware. So while more steps initially lead to better quality, going beyond 6 steps didn't provide much extra benefit and just increased the execution time. This means they found a practical, optimal balance between achieving high-quality densification and maintaining a reasonable computational cost for potential real-time applications. 6 steps was the sweet spot. The impact of diffusion-based generation versus voxel classification was another really critical ablation study presented in Table 4. This experiment directly compared DiffRefine's iterative offset predicting diffusion approach to that simpler alternative we mentioned earlier, a dense binary classification method. That simpler method just tries to classify each tiny voxel in the grid as either occupied or empty in a single step. The results were striking and unambiguous. The diffusion-based generation approach used by DiffRefine consistently and significantly outperforms the voxel classification method for at least 6.592.16 in APBV 3D. That's a huge difference. This strongly validates their core technical choice. The iterative, multi-step denoising process inherent in diffusion, combined with predicting continuous offsets, is fundamentally superior for learning and reconstructing complex 3D object shapes from sparse inputs, especially when used larger, more detailed voxel grids. The simpler classification method, in contrast, seems to struggle much more, likely because it can't capture the intricacies of shape and continuity as effectively in a single, rigid classification step. Diffusion's iterative refinement really shines here. And finally, perhaps the most compelling ablation study, the one that really gets to the heart of the problem DiffRefine aims to solve: the impact of object distance. This is shown beautifully in Figure 8. First, Graph A in Figure 8 visually confirms the problem we started with. It plots the average number of object points against the object distance from the sensor. As expected, the number of points representing an object drops off significantly as it gets further away. This quantitatively confirms that core sparsity issue for distant objects. It also shows that there are simply fewer objects detected at greater distances overall. But then Graph B reveals the true triumph of DiffRefine. It plots the detection performance, AP3D, against object distance for both a baseline method, ST3D, a strong competitor, and DiffRefine hours. What you see is dramatic. While the baseline performance drops sharply as objects get further away, beyond 20-30 meters, DiffRefine maintains a significantly higher accuracy level even at greater distances, out to 50 meters and beyond. There's a clear and growing gap in performance between the baseline and DiffRefine as distance increases. This is direct, compelling evidence. It shows that DiffRefine isn't just improving average performance, it is specifically and effectively tackling that core, persistent challenge of detecting sparse, distant objects, which has been such a major bottleneck for reliable long-range perception in autonomous systems. It excels exactly where previous methods struggled most.
Key learnings and practical implications.
Wow. Okay, after that incredibly detailed journey through the problem, the solution, and the proof, what are the big takeaways? What are the key learnings from this deep dive into DiffRefine by Sang-Yun Shin and the team? For us, the learners trying to understand the cutting edge of AI, and maybe more broadly, for the entire field of AI and autonomous systems, this feels like it offers some really profound lessons about perception and robustness.
You're right. This work truly presents not just an algorithm, but a powerful approach for tackling a critical problem in 3D object detection, particularly with an eye towards real-world deployment of autonomous systems like self-driving cars and robots. There are several key learnings that really stand out, and I think they have implications that potentially ripple far beyond just LiDAR perception. Key learning 1, the transformative power of diffusion for detail reconstruction. This, for me, is perhaps the most fundamental insight. The ability to reframe the problem to treat sparse sensor data, those few scattered points from a distant object, not just as poor data, but as a noisy representation of a complete dense object, and then to leverage the power of diffusion models to iteratively denoise it. That's a genuine game changer. It fundamentally shifts how we can think about filling in missing information in sensor data. It shows how these incredibly powerful generative models, which many people still primarily associate with creating cool images or text, can move beyond artistic generation to significantly enhance perception in safety-critical real-world applications. Think robotics, drone navigation, maybe even medical imaging or augmented reality where data might be incomplete. By learning to predict those 3D offsets and applying differentiable warping, DiffRefine demonstrates a way to dramatically improve the recognizability of partially observed or distant objects, effectively turning potential guesswork into confident detection. It's about reconstructing reality from noisy fragments. Key learning 2. Context is king still for avoiding AI hallucinations. This might sound obvious, but the way DiffRefine implements it is crucial. The explicit integration of spatial context features checking if the generated object makes sense in its surroundings is absolutely vital. As we discussed, it's simply not enough to generate a perfect-looking, dense set of points for, say, a car. If that car is generated floating in the sky or inside a building in the simulation, it's worse than useless, it's dangerous. This principle of leveraging contextual cues like knowing a car belongs on a road, a pedestrian on a sidewalk, or correlating the object with surrounding static infrastructure to actively prevent AI from hallucinating false positives is a critical design pattern for building robust, reliable, and trustworthy AI systems. It highlights that the scene around an object is often just as important as the object's intrinsic features for accurate perception. This lesson applies across almost any AI domain where context influences interpretation, not just 3D vision. Key learning 3. Bridging domain gaps for real-world deployment is achievable. Domain shift is one of the biggest headaches, maybe the biggest headache, in deploying AI models trained in one environment into the diverse, unpredictable real world. DiffRefine directly tackles this challenge head-on. By making the AI models inherently more adaptable to different sensors, like varying LiDAR beam counts, different point cloud densities, and diverse operating conditions without needing extensive retraining for every new environment, this research significantly smooths the path towards truly global deployment of autonomous vehicles, delivery robots, and other advanced perception systems. This adaptability means an AI system can potentially learn robustly in one set of conditions, maybe using simulation and some real data, and then perform reliably almost anywhere, even with sensors it hasn't explicitly seen before. That's incredibly important for scalability, cost effectiveness, and ultimately safety. It's worth noting again that this work was supported by an Innovate UK grant called ScanSpot, which really highlights the strong connection between this kind of academic research and the real-world drive to solve practical industry problems. Key Learning 4. Targeted enhancement offers efficiency and practicality. I think this is also a really important practical takeaway. Instead of trying to do something computationally massive, like trying to densify the entire scene's point cloud all at once, DiffRefine takes a much smarter, more targeted approach. It focuses specifically on proposal-specific point generation. It uses the initial rough guesses from the first stage detector and zeroes in only on those regions, those proposed boxes, where an object is likely to exist but might be too sparse to confirm. It only applies the computationally intensive diffusion process to these small, relevant volumes. This targeted approach offers an incredibly efficient and effective solution. Furthermore, it's explicitly designed as a simple additional module before second stage refinement. This means it's potentially quite easy to integrate into many existing two-stage detection pipelines without requiring a complete architectural overhaul. It's compatible with most existing detection models for two-stage detection, according to the authors. This modularity is a huge advantage for practical implementation. Engineers working on real systems can potentially plug in something like DiffRefine and gain substantial performance improvements, especially in challenging scenarios, without throwing away their existing infrastructure. It's a testament to smart, focused AI design that delivers impact efficiently. For anyone building perception systems, understanding this kind of modular, high-impact enhancement is key, something the AI coach by Anil Nathu aims to facilitate.
This really has been an incredibly insightful deep dive. We've gone from the fundamental problem of sparsity and domain shift through the clever mechanics of diffusion and context fusion, all the way to the impressive results and key takeaways. It's a very technical area, but the implications, especially for autonomous driving safety, are just immense. Making AI perception more robust, especially for distant or poorly sensed objects, could genuinely make our roads significantly safer. And achieving this kind of precise, reliable AI, even when the input data is imperfect, is exactly the kind of progress we love to explore and break down here through the AI Coach by Anil Nathu, distilling this complex, cutting-edge research into understandable, actionable insights for you. Outro. Well, this deep dive into DiffRefine has truly shown how innovative AI approaches like borrowing ideas from generative diffusion models and applying them cleverly to point cloud densification are really pushing the boundaries of what's possible in machine perception. It's a fantastic example of how creative thinking, combined with rigorous engineering, can solve persistent, really hard, real-world challenges, essentially turning what seems like noise or insufficient data into valuable, actionable information.
Absolutely. It highlights a crucial theme. By deeply understanding the nuances of the data itself in this case, sparsity in LiDAR returns, and then employing intelligent techniques like targeted densification, coupled with that all-important contextual awareness, we can make our AI vision systems far more robust and reliable, especially when they face those challenging, unpredictable, real-world scenarios they're inevitably going to encounter. It's a step beyond just recognizing objects towards truly understanding them within their dynamic environment, even when the initial picture is incomplete.
We really hope this detailed exploration has given you, our listener, a much clearer picture of how this kind of cutting-edge research is actively solving critical problems in AI perception. It's moving us steadily closer to a future where AI can see, interpret, and understand its environment with unparalleled accuracy and reliability, even when objects are blurry, far away, partially hidden, or scanned by different types of sensors.
And for you, the learner, perhaps the most important takeaway is appreciating how seemingly small improvements in benchmark metrics, those few percentage points in APBV or AP3D we discussed, can translate into significant, tangible, real-world benefits, especially when it comes to the safety-critical domain of autonomous systems. Every missed pedestrian or cyclist that DiffRefine helps detect is a potential life saved. Maybe also consider how these core principles, the idea of actively addressing data imperfections like sparsity, reconstructing missing information intelligently, and always leveraging context to prevent errors, how these could potentially apply to other data-driven challenges you might encounter in your own work, your studies, or just your general interest in AI. The ability to make sense of incomplete data and use context for robust reasoning is a universally valuable skill in the world of AI.
Thank you so much for joining us today for this deep dive. Visit the AI Coach website for more AI insights.